Gunadasa, the chairman of Green Building Council. And he has invited me to do a presentation here, a green talk here on AI. So I'm upset about it because I don't know much about AI. I'm not an AI person at all. But I'll try to do my best here. What I am actually is I'm a designer. So these are tall buildings I have designed. So I will start with talking about designs. So by the way, our theme is design technology of future towards solving climate crisis with AI. So AI is the final thing I'm going to talk about. We are talking about design technology. Right. So it is all about designs. And for nearly 20,000 years until 1,800s, for the sake of it, maybe the entire human civilization period, what are the things we have designed? So for example, we have designed door locks in those period before 1800. So it's a fantastic design, isn't it? So earlier, imagine you don't know, there's just a door, and suddenly you can lock your door, and then it's your private thing, and so forth. So it's a great design to design locks and then innovate locks. They have designed arrows. So instead of throwing stones and so forth, you can neatly throw an arrow and do the hunting. They have invented swords. The scissor is a great invention, and even coconut grinders. Bullock cart is a great invention, isn't it? So with some wheels and connected into a cart, then you can, without your intervention, you can carry things. So it's a great innovation. People have innovated needles, and then what are these things? This is a catapult. So you can use this. You can load some stones here, and you can throw the stones with this on castles and ships and destroy them. So these are innovations that happened before 1800s. But for last 200 years, what are the designs you see? What are the innovations you see in the world? So from steam engines to diesel engines, to petrol engines, to jet engines, to rocket boosters, from aeroplanes to fighter jets, to rockets, to space shuttles, to even space stations. We have from cannon guns to machine guns to war tanks to we have the rockets to the missiles to atomic bombs. We have satellite discs too. This is Hubble telescope to James Webb telescope to space probes. We have MRI scans to stents to prosthetic limbs to bionic eyes to antibiotics, from calculators to chips to this is quantum computers to robotic arms to then the modern day massive supercomputers. So we have unprecedented plethora of creations and designs we see within last just 200 years. The problem is what powered this design revolution. So it wasn't there for 20,000 years. So for the sake of entire human civilization, it wasn't there. And suddenly we see this kind of a revolution in design happening. So people have designed many things within such a small period of time. So what powered this design revolution? What was behind that? To understand that, we will think about the ancient design technology. So for nearly 200,000 years until before 1,800, there was slow progress in designs because there wasn't such a design technology available. So let's say this is a castle. So we want to destroy it with a caterpillar. So this is a caterpillar and how to design the right size of a caterpillar. So there's no way to do it. The only way is you can do it with your experience. or do it with trial and error. You build one, and if it is not working, you have to build a bigger one, and then if not, another bigger one. So that's how you can find the right size. But after 1800s, actually 600s, with the support of the ideas of Galileo and especially Isaac Newton, we understood that the world works on simple mathematical relationships. So F equals NMA is the way apples falls, and it is the same way, the same formula applies to rolling balls. And it is the same formula that works even in case of planets orbiting the sun. And it's the same formula that works in the blood flow in your veins or the river flows. Everything is governed by simple mathematical relationships. So we understood the world is mathematical. It works in that way. So that was the thing that started this design revolution. And for example, say this is a slingshot. So this is a stone I have with mass m. So if I have to throw it to a height of h, how long should I drag this slingshot backwards? So let's say the force is a constant and the force I'm dragging is f, and the required distance is y. So it's very simple. You can calculate it because the work done here when you drag this backward is the force times the distance. It is Fy. With the same principle, when the stone moves up, the force acting on it is mg, its weight, and the distance is h. So the work done or the energy stored there is mgh. So these things are equal. So Fy is mgh. So with this, you can design everything about this. For example, if I want to design a rubber band for this slingshot, so let's say I can understand what is f should be if the y is a constant. And if I want to throw, let's say, a bigger stone, what is the height it is going to reach? With the same thing, we can calculate. So suddenly we can calculate. So without building up things on paper, people can do things. So this is true as far as h is a small distance, like the height of a mango tree. This works. So if h is a distance from Earth to Moon, it doesn't work because g, the gravity changes. So that is the reason. So with this, designers can calculate and quantify things, and you can so accurately the design the size of a caterpillar kind of a thing to destroy a castle, and you can do it in much accuracy on paper. So what if I have to throw this stone so that it will never return back? How to calculate that? So I'll simplify it. So this circle is the Earth, and this is the center of the Earth. I'm measuring distance from that, and this is the stone we are going to throw. So the energy is not now mgh because we are throwing it to the infinity. At the infinity, the gravity is 0. Gravity is 10 on the surface of the Earth. So it changes. It governs by Newton's equation of gravity. I think all of you know that, but I'll just explain. F is the force between this stone and the Earth, this force. G is a constant, m is the mass of the Earth, and simple m is the weight of this, the mass of this stone. X is the distance between this stone and the Earth. So as the x increases, when the x goes to infinity, this becomes 0. So how to calculate it? It's difficult to calculate because now g is changing from place to place. So that's where this Leibniz and Isaac Newton came with this brilliant idea of calculus. So with calculus, you can do such things. For example, now this is sun and this is a planet orbiting the sun in an ellipse. So gravity or the force on this mass is changing from place to place. When it is at A, it is very high because it is close. When it is at B, it is lowest. In between, it changes in different ways. But we have no problem in calculating its trajectory, its velocity at each location, and everything about it. So how to do it is very simple. I think everybody knows it. So we'll consider small distance traveled by this mass, like the height of a mango tree. Let's say it's delta x tau without using h. So force acting on this is this one we discussed. And we multiplied force by the distance traveled, delta x, and we get the amount of work done or the energy to go a small distance. So what calculus does is we can add these small distances starting from the surface of Earth to the infinity. So we'll add them up together and we'll get the total energy. So that's what calculus is all about. And the advantage of this kind of thinking is with this, you can design things. With this, you can actually design a rocket to escape the gravity. So slingshots doesn't work. So you can calculate the amount of energy you can release with a slingshot. And when you calculate this, you can't do it. So because earlier what happened was people have to throw stones up faster and faster and then see whether it's going to infinity. So now we don't have to do it. We know our target. We know where we are going. Diesel engines doesn't work. The catapulters doesn't work. We have to have a specific system, and with this knowledge, we can design that system. So we have to have rocket boosters, and we have to have a small payload to carry. We have to have such a huge amount of a tank of fuel and so forth. So all that can be calculated. So that is the thing that triggered this design revolution we have. So right now, the designers can calculate and quantify many classical systems. For example, the dams we can calculate and design, the air balloons we can calculate and design. So many things people can calculate and design and do it on paper. So I said classical system. So why I said classical? Classical means things that are of our size of human beings or size of the solar system kind of things. So if anything moving at a faster speed closer to the speed of light, we can't use F equals ma kind of scenario. And for quantum systems, they don't follow that rule. So we need something else. So that's what this monstrous equation did, the Euler-Lagrange equation. I think some of you might have gone through it, but for many, it can be kind of a very monstrous thing. So we will try to demystify this and try to make little sense out of it. We look at what this equation says. Right here, we have a term Qs of phi. The Qs of phi is the coordinate system. So it is XYZ coordinate system, but it works for any kind of coordinate system. Maybe polar coordinates, maybe parabolic coordinates, whatever the coordinates you choose. This is a very, very general equation. It works for any coordinate system. But for our purposes to understand this, we will think about one direction. So it is X. So this term here within brackets is saying a scripted L kind of a thing. This gadget, we will discuss what it is, this scripted L, the change of it, the rate of change of it in relation to position of something. That's what this term says. And here we have a much more monstrous term. It's not only Q sub I, it's Q sub I dot. It's a time derivative of Q sub I. But now we know what it is. Q sub I is the direction X. So the rate of change of it in respect to time is its velocity. So this is velocity. So this side, we are talking about this scripted L kind of thing, how it changes when velocity changes. And we are talking about the time derivative of this. So this is what Euler-Lagrange equation is. And this scripted L is called the Lagrangian. It can be anything. It's a function that depends on positions and velocities. And in classical mechanics, Lagrangian is the difference between kinetic energy and potential energy of a system. In relativity, it's the space-time interval. It is x squared minus t squared in our case. And it means different things in quantum mechanics and so forth. But it's something general. So we can, I mean, it is possible to prove that what this equation talks about is nothing else but F equals NA, the same thing, but it's in a very general terms. It can be applied to everything. So Lagrangians. So all kind of physical systems that is known to us can be described with a Lagrangian. So that is the important thing. And waves we can describe with Lagrangian. The electrodynamics can be explained. Quantum mechanics works with Lagrangian, and most importantly, the standard model of particles work with Lagrangian. So this is a pivotal thing, like F equals NA, that gave a lot of power to the designers. I say the standard model of particles, this is the greatest discovery of mankind ever done. I think most of you have some understanding what it is. The thing is, this standard model, entire thing can be represented with a single Lagrangian. So if you write it on a piece of paper, it will most probably take one A4 sheet. So such a small thing is this standard model, but it explains everything that happens within our solar system. For example, within the limit of the solar system, everything we can explain. So there are a lot of particles it describes, but to describe the world we live in, we need only very few. So these are called quarks. So an up quark and down quark with the gluon creates what we call a proton. And two down quarks and up quark makes a neutron. And we have electrons. So I'm talking about 1, 2, 3, 4 particles that makes all the elements in the periodic table. So with this Lagrangian, we can explain everything from hydrogen to helium to lithium, anything, its properties, how it works, and everything based on this. And to describe our entire world, we need only one more particle. What it is the light, the photon. So with this, with Lagrangian, any phenomena happening on the world, we can explain the wetness of water, the freezing temperature of water, to the amount of power released by a nuclear bomb. Anything we can calculate and prove with this single mathematical model called the standard model. So what's the result? The result is designers can do designs of another level. So they have done it. For example, the quantum computers you're talking about is a result of the standard model, and the advanced microchips you're talking about, the nuclear fusion reactors, the atomic, for example, systems like this, you model and redo DNA kind of things. All those things are governed by this. The nuclear fission reactors, the carbon nanotubes, nuclear fusion reactors you're talking these days, and also the superconductors. And from that, we have the CAT scanners, and then the maglev trains. All those things are working thanks to the standard model. So all that is we call pencil and paper mathematics because we can calculate everything on pencil and paper. For example, if this is a pendulum, with this system, we can calculate everything about how this pendulum works with equations. So if this is called two-body problem. So when there's two celestial bodies like this, the path they are going to take under their own gravity, we can calculate. And also, in case of black holes, everything people have calculated from infinity, at least to its event horizon, what's happening, we can calculate. But there are things that is totally outside of this system. For example, three body problem. So these are three bodies moving under gravity. So how they work, it's difficult to do with that. And then this is a pendulum. One pendulum is attached to another one. So two pendulums are hanging when you hang it. This is the kind of behavior we see. So these things are difficult to be explained with this kind of mathematics. It's difficult to calculate this behavior. So, but today, you can do it with computers. The system is called numerical integration. It's a new system. I think most of you have worked with it. How we do is, at a given position, we know the status of the system. We know the velocity and the position of each particle, and then how gravity works on each one. We can calculate for that particular moment. And with moment after moment after moment, we can build up the trajectories of these particles. So it is possible to do with computers. So if you are to do it with pencil and paper, it will take a lot of time. So this is how we dealt with complex problems today, like fluid flows and so forth. We identify the parameters of the problem, we build them up into equations, and we'll give it to a computer to solve. So that is how we do, and we can adjust parameters, play with the parameters, let the hard work done by computer, and we can see how the system behaves. So that is all about the modern design technology. So I'll explain how today we design things. That is the important thing. So this is what is behind the designs, but how we design things today, not 10 years ago, today. So today, designing is all about modeling relationships between things. I'll explain with this kind of an illustration. So this is a sun. Its mass is m. And this is a satellite. And its starting position and velocity is given. And then this is the trajectory of the satellite. So it goes around like this in the sun. And the thing is, we can play with m. We can change m and give different values to m, and then we can design the path of the satellite. So how to do it? So this is important when we design something. Today, this is how we do it. We set up the playground to play with this. So that is how we start to do it. We identify things that predominantly govern the form of this trajectory we have to design. F equals ma is one thing, and then the Newton's law of gravity. We discuss about this. F is m is the mass of the sun, simple m is the mass of the satellite, r is the distance between them. So these are the basic two governing laws of this particular problem. We'll omit other things, and then it's easy. This force on satellite by the sun is the same. So we make them equal. M cancels off the mass of the satellite, and the trajectory of the satellite is described by this simple equation. Acceleration is the mass of the sun divided by r squared, the distance squared. So this simple thing sufficiently explains how it works, and this governs the form of this trajectory of the satellite. So designing this trajectory of the satellite is all about modeling this relationship between acceleration, mass, and the radius r. So how we do it? We model this relationship, give it to a computer, and then let the computer do the calculation. We start play with them. So we will give different numbers to him, and then see how the trajectory changes when we change them. So when m is very high, this satellite will spiral into the sun like this. When m is an average amount, it will be a circle, and when m is low, it will be an ellipse, and when m is very low, it will be a parabola like this. So as we change M, when we start playing with them, we can create different trajectories. We can design different trajectories. So that is how we design things. For example, this is a building we have designed such a way. This building reacts to gravity. So there are reasons why it should stand up and then to capture views and get ventilation and so forth. And when the gravity is low, this is the form of the building. And as the gravity increases, it comes down to a form like this. So until recent times, complicated design solutions are out of the system. You can do simple things like that only. For example, buildings are complicated things and parameters that govern the form of a building is not only gravity. So for example, when it comes to building, the land value, the climate, the land form, budget, and many things affect the form of the building, and we should consider all of them. And therefore, relationships are complicated. And if you write an equation describing all these relationships, it will be a very complicated equation. So when we can't do with equations, what we do, we draw diagrams. So that is what we learned from Richard Feynman in quantum electrodynamics. When things are very much complicated, he came up with this idea of representing everything in diagrams. So we have today visual programming languages, and architects and engineers design things, complicated things with them. So each kind of box here in visual programming language is a mathematical equation. And you can put into that scalars, vectors, fields, and many things, and the geometries, and equation works, and you can take the results out from the other side, and you can give it to another equation. So likewise, we can create a complicated network of equations like this, and with that, we can design things. So that is all about parametric design. So that is how parametric architects especially design buildings these days. For example, this is a project we started doing at Colombo Port City. So the height of this building, we have made a parameter, and you can see as the height increases, it's not just beautifully increased, but for example, if you look at the lobby space at the ground floor, as the height increases, it has to be increased. So it automatically reacts and increases everything. So it's the visual programming language, things are set up in that way, so it reacts like that. This, when we change the form of the building like this, it's not just hanging in the wind. You can see it follows a certain pattern. If you look at these windows, as the width of the floor plate increases, you need more light and ventilation to the building, and it opens up windows, and as it retries, windows disappear. So everything is, you can program everything like that, everything can be connected, and when you change the parameters, you can play with it. So this is a direct application of climate to the building. So as the climate changes, when you need more shading to the building and more openings in a tropical kind of climate kind of a thing, you can see this building reacts and it opens up windows and it creates overhangs. And when you change the climate to a colder climate, it closes down and then windows disappear. So as the context change, the proportions of the building change, the parameters change, the building take different forms. So that is how the parametric designs are done, and that is a state-of-art way of designing things today. But since these parameters are complicated and so forth, today we barely can set up this playground we are talking about to play with these parameters. And very few architects and engineers use it, and it's not used much today. So that is the brief history of past 200 years. How people design, how we design things, that is the design technology. And there's not much of a change. The principle is we know the world works on mathematical relationships, and those relationships can be dealt with differential equations. So that's the base of this design technology. And although we have such a huge revolution of designs, that is the base, and it has not changed much. For last 20 years with computers, there is a slight improvement with the numerical integration and parametric design, but it is not much of an improvement as such. So there are things we fail to deal with this with this system. For example, complicated things like animal brains. So with this system, we can't explain anything about animal brains. And the other thing we fail to deal with is the climate problem we have. So I would say we have failed to design a solution to the climate problem. Some of you might not agree with me, but I'll explain why I say we have failed to design a solution to the climate system. Okay, so we will discuss the climate crisis. We all know. I'll simplify it. It is a problem about carbon dioxide. The other problems we'll keep it aside, since this is the main problem. So we have carbon dioxide in atmosphere than the required or the norm, and that is the problem. How many of you know what is the percentage of carbon dioxide in our atmosphere? We have a huge problem of it, isn't it? Is it 20% of atmosphere? Is it carbon dioxide now? Or is it 2%? Yeah. So this is the number. So you can see 78% of our atmosphere is nitrogen. These are rounded numbers, so if you add them, they will not add 100. We have 20% oxygen and 2.5 water vapor, and approximately 1% argon. And actually, carbon dioxide in the atmosphere is only 0.04%. It's such a small amount of carbon dioxide that there in the atmosphere when you calculate it. And the second thing is, who creates this carbon dioxide in the atmosphere mostly? Is it the nature, or is it us? So have we created about 80% of carbon dioxide in atmosphere, and nature has created only 30%? Is it the ratio? Actually, it's what we have done is we are minute creatures in the scale of the Earth and the global scale. So you can see about 96.5% of carbon dioxide in the atmosphere is due to natural sources. And we have created only 3.5% of it. So 770 billion megatons of carbon in the atmosphere are generated by natural systems per annum, and only 40 billion of metric tons are created by us. The thing is, the ocean creates a lot of carbon dioxide, about 330 billion metric tons, but it absorbs more than what it creates. It absorbs today about 340. The vegetation, lands, and animals produce about 440 billion metric tons of carbon, but they absorb about 450. So that is the balance of carbon in the atmosphere. So this graph shows it everything. So this is the additional carbon we are creating. So we are creating by burning fossil fuels and change the land use. This above zero line shows the things we have created. And then this is how it is sunk. The ocean has a sink, the land has a sink, and the atmosphere takes only a small portion of it. So with this intervention of human beings, now we have a problem. The global carbon dioxide in the atmosphere has risen above 40 particles here per million particles. So that is the problem people say. And if you look at the history of 800,000 years, the carbon dioxide level has never been that high in the atmosphere. The problem, you know, what happens when there's a lot of carbon dioxide in the atmosphere, it creates greenhouse effect. So I'm not going to explain. I think all of you know that. And temperature of the world increases because of that. And the scientists say there's a red line for this. So it's 1.5 degrees Celsius increase from the 1950 levels. And if the global temperature increases more than this, there will be a crisis. There will be a catastrophe that is going to happen. Beyond that point is things are not reversible. So right now, if we stop emitting carbon dioxide to the environment, it might take some time and recover. But if you go passing this level, there's no return. So world is going to move into a catastrophe. Beyond that level, there's no recover. Beyond that level, the world will never be the same. So why we say world will never be the same when we pass this red line? One reason is the melting of glaciers. So this is the Arctic glacier. So if this global warming continues and if it passes this red line of 1.5 degrees, this Arctic glacier will melt down and we will see a ice-free Arctic by 2050. So what's the problem we have with this glacier melting down? Why it is a catastrophe? You will say sea level rising, but we will forget that in terms of temperature, it has a huge effect because this white color of the earth reflects sunlight back to the space and then it keeps the earth cooling. So the color of the earth's surface is something very important to the temperature. For example, the model shows, so if you make half of the earth cool, if you cool down and make it into ice, what will happen next time? What will happen is it will keep on cooling forever because we have more ice and a lot of solar radiation will be reflected back. Earth will be cooler and it will increase more ice. And we will face endless winter kind of a thing. So entire globe will be frozen if you do that. So you might ask me, then the solution to the climate problem is if we can paint the earth, a considerable portion of it in white color, it will solve the problem. We are talking about the global warming. The answer is yes, it will. And there are proposals for that. For example, there's a proposal to spray this diamond dust in the upper atmosphere, so it reflects sunlight back, and it will cure the climate crisis we are going to face. But those are not practical or financially viable solutions right now. So these glaciers melting is a problem. Right. Then the second problem is when you go passing that particular target of 1.5 degrees, the permafrost in northern and southern hemisphere start to melt down, and they contain 1.7 billion metric tons of carbon in terms of methane and carbon dioxide. So if you compare numbers, the annual amount of carbon dioxide we are emitting to the atmosphere, not we, the entire amount is about 770 billion. This is including the nature and us, everything. So here we have 1.7 billion metric tons of carbon dioxide at once emitted to the atmosphere. So it is going to be a catastrophe. So after that, there is no return. So it's a non-return point. And with the climate change, when the temperature rises, the biodiversity collapsing will happen. And what will happen is in the sea, this phytoplankton, for example, this bacteria in the seawater is the thing that absorbs and digests carbon dioxide as much as possible. And they are going to die. And then the oceans will not be a carbon sink anymore. It will be a carbon emitter. And the same thing will happen to the forest. For example, this Amazon forest, and when they calculate right now, it's not no more a carbon sink, it is a carbon emitter. So with wildfires and all those things, due to this climate change we are facing right now, it emits more carbon dioxide than it absorbs. So yeah, the failure has already started. So this is the remaining carbon budget. So we have consumed 2,590 gigatons of carbon dioxide into the atmosphere, and only 200 gigatons is there for us to add to reach 1.5 degrees Celsius. And after that, there will be the catastrophe. So that is the situation we are facing now. The problem is how far is this red line? So how long is there? The IPCC says you have to do it now or never to avoid climate catastrophe. Unless we do something and change it right now, the catastrophe cannot be stopped. And the thing is, we have brought the world to an end like this. So we have rolled it up to inflection point like this, and it is about to fall over. And how to stop it. The data shows very clearly this is the plan that is agreed in the Paris Convention and many places with the governments, and all that has failed. So the governments and the companies are expected to reduce the world carbon emission like this, but this is the trend we see. So carbon emissions are still increasing and they are not decreasing. So this climate crisis there's no way to stop it, although we are talking about optimistic things. The thing is, we have failed to design a solution to climate crisis, may it be a technical solution or a diplomatic solution. So we have totally failed to do that. So that is the truth. So on top of that, we actually don't understand how climate works also. So this is the global temperature from 3 billion years today. So you can see there are fluctuations, ups and downs happened for 3 billion years. So if the climate models you are talking about here are right, so when you run it backward, we must see this pattern happening, but we don't notice that at all. So we see only straight lines kind of things. So there's something totally wrong about the climate models you are talking about. So only explanation we have about it is this Milankovitch cycles. So what Milankovitch showed is that the Earth's orbit is not always a constant because of other planets are presenting. It's not a two-body problem with Sun and Earth because other planets are there. Sometimes with the gravity of other planets, the speed of the Earth decreases. And sometimes they drag it forward and it increases. So there are cycles. At some periods, the Earth acts as almost a perfect circle, and sometimes it acts as an ellipse. So this cycle changes in 100,000 years kind of a period. So sometimes when it is an ellipse, at certain period it's very close to the sun, and certain period it's far away from the sun. So that changes the intensity of seasons on Earth. And he has shown this tilt of the Earth, this 20 to 20, this angle of the Earth, 23 degrees. It is not a constant. It is constantly changing from 22 degrees to 24 degrees time to time. The cycle takes about 41,000 years. So with that change, what happens is this difference between the amount of sunlight received from northern pole to southern pole, those things change. And also this axis is at a precession movement. So it is rotating like this around the central axis. So this precision movement takes a 26,000 years cycles. So with the combination of these things, he says he has shown that the climate of Earth changes. But the thing is, that is the Milankovitch cycles. And it's not consensus. So we don't know whether it is the case and so forth. So according to him, that is the reason we have these ups and downs, and we haven't considered any of those things in our climate models you're talking about. But the Milankovitch cycles doesn't fully explain this temperature patterns we notice. So it's not taken as 100% correct now. And the temperature of the sun surface actually is not a constant. It changes time to time. So there's a 0.1% change happening in 10 years periods. So it's not, we don't know when it happens, when it doesn't happen. But the thing is, there's noticed pattern that this El Nino and La Nina phenomena is related to the temperature changes in the sun. So there's a pattern recognized, but we don't know how it works and so forth. So we don't fully understand how climate works, and our climate models doesn't fully explain the situation. So even in the previous slides, I show the risk and so forth. You can see the risk they are saying is 50% chance is there. So 50% chance is there that this climate crisis will not happen. So we don't know, our models are not accurate. And also we don't know whether the climate change is a good thing or a bad thing, although we think everything is so bad about it. So one thing that happens with this global warming is, now this is the existing way the wind patterns works. I'll explain the central Hadley cell only. So what happens here is, at the equator, this is the equator, the hot air rises. At the equator, hot air rises, and as the hot air rises, they cool down and they form clouds, and a lot of rain happens. So that's why at the equator we get a lot of rain. And this hot air that has risen up goes towards the poles, and at the midway they turn down like this and then come back. So this is a cycle. So in this particular area, what happens is, as this hot air comes down, so you can see all the rain it contains, clouds now has gone. So this is dry air coming from the sky. And you have here the desert atmospheres right here. So we see deserts in this particular region. So with this climate crisis and global temperature rise, what will happen is this cycle will be intensified, and a lot of air will rise up, and the rain happening here will be increased, and then this Hadley cell will move towards pole further. So that will push this circle towards poles, and the deserts we are talking about are going to grow towards the poles. So is it a good thing or a bad thing? But what you can notice is, as this region goes toward the pole, because this is a sphere, the land area taken by these deserts are going to decrease little by little as it goes towards the poles. So this is, for example, the Sahara Desert some time back. And do you know, this is what is happening to Sahara Desert now. Sahara Desert right now receives more than 500 times more rain than it was earlier, and it is now growing like this. And these are very recent photographs. The lakes formed in the Sahara Desert, and then the rivers and all those things are now once again activating after millions of years. So we don't know whether the climate change will be a good thing or bad thing. Our models doesn't perfectly show that. So the thing is, with the limits of current design technology, we have failed to deal with climate crisis. This is where the Earth today, and we don't know. We think about 50% chance it will fall into a bad pit, or it might fall back to where it is. Because if you look at this Milankovitch cycle, it shows ups and downs and ups and downs, and what we are seeing right now can be a typical up, and right after that it is abrupt drop of temperature. So we don't know whether it is going to happen or not, and we don't know there will be a change, but that change is a good change. We don't know that. So this is where we are hanging now, and the thing is, within next 2 years, there might be a massive change in the design technology in the world. So we see a change of the design technology for 20,000 years happen in 200 years. So what happened was in 20,000 years is nothing in compared to what happened in 200 years. And there might be a change like that is happening just in 2 years to come. There is a revolution of design technology that is waiting ahead of us. So what are the revolutions we have heard of? You might say industrial revolution is a revolution you have heard of. But if industrial revolution is a revolution, artificial intelligence is not going to be a revolution. AI is going to be an explosion in relation to industrial revolution. It is going to happen so fast and so quick. The thing is, the technology in the world has always been developing, not fast, but exponentially. The problem with the human mind is we are unable to imagine what exponential growth is. So our mind is geared to think anything about linear growth. We are not geared to think about exponential growth. So I'll explain with the example how we fail to understand exponential growth. So this is a 0.1 millimeter thick paper. And when you fold it into two, the thickness of this is 0.2 millimeter when you fold it once. And if you fold it over once again, the thickness will be 0.4 millimeters. The question is, if I fold this for 42 times, so I fold this over and over again for 42 times, what will be the thickness of this paper? Can you imagine? Will you believe if I say the thickness of this paper will be taller than me? It is more than 6 feet. I think no one will believe that with just 42 folds, it will be taller than 6 feet. But do you believe if I say when I fold this 42 times, it will hit the moon? You can do the calculation. It's 0.1 millimeters into 2 to the power 42. And the answer is 450,000 kilometers. Distance to the moon is 300,000 kilometers. It is more than the distance to the moon. We can't imagine it because our minds are not geared to think about exponential growth, because at each fold you are folding, the thickness doubles. So it keeps on doubling and doubling. And at the final stages, unbelievable, massive things happen. The thing is, technology is growing like that. Technology is growing exponentially. Always it has been that, and the Ray Kurzweil is the engineer who first noticed this. And And what he noticed is by year 2000, around 2000, he said, looking at the pattern of the computer technology has grown, that right now it is equal to the brain of an insect. The computing power of an average computer those days was like the brain of a cockroach. But studying this exponential pattern, he said, by 2030, by 2030 kind of thing, it will be something like a human brain. So what he said in a graph is like this. So this will explain it in a better way. This blue line shows the human intelligence, and the red line shows the exponential growth of artificial intelligence. So by 2030, like something important will happen. That is, the processing power of computer will be equal to a human brain. So that is what is called AGI, artificial general intelligence. And according to his predictions, by 2045, something special will happen. That is called artificial superintelligence. That the processing power of an average computer will be more than all the human brains put together. And according to his model, during this period, something important will happen. That means, now look, human beings have created a computer that is smarter than them. Can those computers create smarter computers than themselves? So if they can't do it, how can they be smarter than us in the first place? So definitely those computers will be able to design computers that are smarter than them, and those computers will do the same, and there will be an intelligence explosion happening from this point onwards, and there will be a huge growth of intelligence. And by 2100, this intelligence explosion will consume all the matter and energy in the universe. And according to this model, by 2100, the entire universe will become one big thinking machine. I don't know whether it is true, whether this will happen or not, but what we know for sure is today we are at the verge of artificial general intelligence. And most of us don't properly understand what artificial intelligence is even today. So this is Gary Kasparov in 1997. When we were in the schools, we noticed this event. So IBM Deep Blue computer defeated the world champion, and he lost his title as the world champion in front of a computer. Is this artificial intelligence? Does this has anything to do with AI? The answer is no. There's nothing to do with AI here. It is machine defeating intelligence. Then what is artificial intelligence? Yeah, artificial intelligence is all about digital brains living inside large computers. When I say large computers, I don't mean a little bit bigger large laptops, but these are large computers. So they have huge number of GPUs, billions of them, and they consume huge amount of power, like power of entire or several power stations are consumed by them. So they are arranged in large warehouses. A large computer sometimes consist of several warehouses connected together. So that kind of a huge thing is a large computer. So the seat of intelligence in animals has been or is always their biological brain. And the seat of the intelligence in artificial intelligence, therefore, is an artificial brain. So whether it is natural brains or artificial brains, the building block of a brain is a neuron. So I'll explain what a neuron is. I'll try to explain. So when you know what a neuron is, you know how artificial intelligence works. So that is important. So I'll just try to explain it. So this is a father. I'm going to explain what a neuron is. And his height is X. This is mother, her height is Y. And the question is, what is the height of their son? So if they get married, what will be the height of their son as he grows up? So to answer that, we can build a neural network or a neuron to do that. So how we do it is we take X and we multiply it by an arbitrary number. I'll call it W1. Y we multiply it by an arbitrary number and we put it through an equation. So let's say equation is X plus Y. So we put it through this equation and we get an answer. This arrangement is a neuron. So for clarity, we will put some numbers. So we will think his height is 1 meter and the height of his mother is 1 meter. W1 is 1. I'm just putting some arbitrary number. I don't know what it is. W2, I'll put 1. And we get the answer of 2. So their son's height has to be 2. So this is their son, and we know his height. His height is not 2, it is 1. So there's an error of 1 happening here. So in neural networks, what we do is we identify the error and we send it back to the equation and then calculate correctly what is W1 and W2. So with one family, we will not be able to do it, but with several families data, when you run it backwards, we can accurately calculate W and W2 if there is a relationship like that. So this sending it through back and then calculation is called back propagation, and it is also called training or learning of neural networks. The only difference is at the center is not only one neuron, there is a network of neurons in this kind of calculation. So there are several equations involved like this. So to make things simplify, I'll represent the neural network in a triangle kind of a thing like this. So this is input, this is output, and this is the neural network. So it's easy for me to explain things. So the neural networks, so the advantage is it can learn anything. For example, people have tried to record the noises made by whales, and then they now understand few things about how whales are talking to each other and the language. So they have recorded the bats shouting inside caves and then send that noise through a neural network, and now they at least know each bat has a name for him. And then this is the human genome, for example. So we have recorded everything. We know what human genome is, but there's no single person on earth who can read this genome and then say, this part is related to this kind of a protein and it will fold into a protein like this. But neural networks have come forward and they can now do it. So for example, this AlphaFold by Google DeepMind is precisely capable of showing the protein structures, how the proteins are folding. So translating DNA to protein is easy, but the protein folding is a difficult thing. And I think they won the Nobel Prize this time for chemistry for this discovery. And then computer vision is something important. So before the AI systems come, if you give this picture of a dog to a computer and then show this picture and then say, identify whether this is a dog, it can't do it because each pixel is totally different. So there's nothing related to this one in this one. And even if you show something like this, the computer will never be able to say the difference between these three. And even if you train how to do it, it is not going to look at this and then say this is not a dog. But we can do it because in our mind, we have a concept of a dog developed inside our brains. Neural networks can do the same thing. How we do it is we take pictures of dogs and we have a data set and we put each picture and then the neural network has to say whether it is a dog or not. So if it is a dog, we will, if the answer is correct, we will say yes, it is a dog. Otherwise, we will say no, it is a dog. And we continuously show many pictures of dogs to this neural network, and it gradually learns to identify dogs. And what happens is it is developing a lower dimensional representation of a dog. or in our terms, it develops a concept of a dog. So the advantages of this is, for example, this driverless cars are coming everywhere because these cars now can see the road, see people, see signal lights, and they can see even dogs on the road. So they are getting now everywhere, and they will come to Sri Lanka also very soon. And there's drastic development of robotics based on this because these robots then now can see like us, they can think like us, and they can move like humans. So, for example, the Tesla is saying they are 10% of their warehouse workers will be replaced by humanoid robots by 2025. And other things of computer vision is now computers can see things even we can't. For example, looking at the scan of a human retina, they can identify diabetes level, the blood pressure level, the kidney disease of this person, the liver disease, the gallbladder disease, the Alzheimer disease, and hyperlipidemia. So all this can be identified just by looking at human retina by an AI system, which no human doctor can do. So those are some examples of neural networks. And the other important thing is, can we run these neural networks backwards? So running backwards, what I mean is, after training the neural network, if you put the height of the sun this side, can we get the height of father and the mother? Let's say W1 is 0.5 and W2 is 0.5. Can we get their actual height when you run it backward? Sort of you can, but there's no single answer. For example, 1 will work, but 0 height of father and 2-meter height of mother will also can come. But we know 0-meter height father is improbable. So with the slight adjustment of probability, we can run it backwards and then generate what height of father and mother is. So this is the wonder of it. So that is where generative AI is coming. So we have a neural network trained on dogs. So this is the input. We have trained it, and we have a lower dimensional representation of a dog or a concept of dog at the center. So if you run this network backwards, what will happen? There comes a dog out of it, and that dog is totally different to all these dogs. Thing is, to create this concept of dog, I need not to essentially train it out of pictures of dogs. For example, I can train it with poetry of dog and then create the concept of dog. And when you connect the paintings of dogs trained neural network this way, the poetry get converted to paintings. That is what transform architecture do. So it do text to image. That is the most popular thing. So that is generative AI. Oh, I think you have seen these things. So this beautiful Indian lady doesn't exist. It's a creation out of text to image. So generative AI does many things, poetry to painting, text to image, text to video, and these days it's very popular. Text to image to 3D model, you can do that. So a lot of architects use that. And sketch to BIM is not available right now, but it will come very soon. And text to DNA, text to protein, all that conversions are possible. And the last important thing I'm going to tell about neural networks is these simulations. For example, this is a fluid flow. So if you enter this fluid flow through a neural network, can the neural network predict what is going to happen to this fluid flow at the next moment? We can do it if we train this neural network with a large set of data. So we have records of fluid flows for a very long set of data, and if you train it continuously, it will be able to do that. But the scientists have found there is a better way or easy way of doing it. And that is called PINs. So that is the emblem of my speech today. It is about physics-informed neural networks, PINs. So when you input a fluid flow this side, and when you get an output this side, to check whether this is correct, you need not to have a data set as such, because what is coming from the other side has to be physically correct. For example, mass has to be conserved. The mass that is there has to be here as well. Momentum has to be conserved. So if this is an incompressible fluid, the divergence of this fluid has to be zero. It should satisfy the Navier-Stokes equations and so forth. So if you put x, y, z, and t, that is the position and the time this side, the neural networks takes out the velocities UVW and the pressure, and then we can calculate all other parameters to check it. So that is what this LLMs do. And then one such parameter we can check is the Euler-Lagrange equation we talked about. And then the most important thing we are talking about is the SINDs, a type of physics-informed neural network. I'm not going to explain what SINDs means. It's the first identification of nonlinear dynamics. But what it does is, when we show it position and time of a system, for example, an apple falling, it studies it, and then it sets out the equation that governs that. So if you show an apple falling, it can generate F equals ma. So people have tried several complicated systems out of it, and it has correctly modeled the governing equations behind the system. So we just put in a video of a system, and it identifies the governing laws or the laws of physics. And then the most important thing is we have Lagrangian neural networks now. So same SINDs, but what happens is when you input the positions and velocities, it spits out a Lagrangian out of it. So this is the standard model we talk about. So it has a simple Lagrangian that fills out a single page. And it's not a simple thing, although it has been a work of a century and tireless work of the best human brains ever born. It's work of Einstein, works of Niels Bohr, works of Paul Dirac, works of Schrödinger, Heisenberg, the Feynman, and also Stephen Hawking, and thousands of more scientists. So it's a work of decade. So with this new development of neural networks, this kind of a revolution can happen in a fraction of a second in near future. So we will be able to model and interpret complex system like human brain or climate very soon with these systems. So for last 200 years, the design technology is this. We understand the world works on mathematical relationships, and we can deal with a fraction of it with differential equations. So that's what we know about the world right now. But in a few years to come, what we'll see is we can deal with all of it, not a fraction of it. And no matter how ever complicated it is, we can deal with it. So that level of an advanced design technology will trigger off an unprecedented design revolution. Design to reverse the climate crisis might be possible. So that's it. So we don't know whether it will happen or not. Don't ask me whether it is going to happen. I believe it. I don't know. But the thing is, we have brought the world to such an unstable position right now. And it is the only hope we right now have. Okay, so that is my talk. I took more than 1 hour. So it is about design technology of future. I think you understood something about it, and towards solving climate crisis with AI. Right, that's it. Okay, thank you.
Thank you, sir. And now is the perfect time to engage with our audience. If you have any questions, please feel free to ask them now. I think there is no any questions, sir.
Yeah, because we have taken about 15 minutes more also, so we will stop here. Okay,
Yes.
right.
And thank you, Architect Nirodha Gunadasa, for being with us today. Your expertise and innovative insights into the interaction of artificial intelligence and climate solutions are invaluable as we explore the role of technology in shaping a sustainable future. And we are excited to learn from your deep knowledge and visionary approach to tracking one of the greatest challenges of our time. And thank you for guiding us through this transformative journey. And finally, to our wonderful audience, thank you for your active participation and enthusiasm. Your engagement is essential in driving the collective action needed to create a cleaner, more sustainable future. And thank you. And we look forward to seeing you at our next Green Talk. And thank you so much, sir.
Thank you very much. Okay.